Can you hear me, Dr. Vute? I guess. Can you hear me, Professor Vute?
Yes.
Okay, that's good. I'm Nimadana, a moderator also by the name of the Education Committee, Dr. Pshtiwan, and on behalf of the esteemed President and Vice President, Professor Omar Karani and Professor Sirwan Zahawi, and Executive Manager, Dr. Saman Abdullah, I would like to officially open our second international workshop by the ACI Kurdistan chapter in the American University of Soleimani at Iraq. And I would like to send my thanks to Dr. Adam for organizing the auditorium room for today. And I hope this event would be useful for engineers and also academics in the Kurdistan region. So without further delay, I would like to introduce the first speaker for this occasion. And before we start, I appreciate it if you put your microphone on mute for the guests that are joining us online via Zoom today. So I will be waiting to put their microphone on off. So I would like to introduce the first speaker of our workshop today, Professor Vute Sirivivatnanon. He's a professor of concrete engineering at the University of Technology in Sydney. He worked as a bridge design engineer and quality control engineer and principal structural engineer before joining the SIRO in Australia. And Dr. Vute has conducted his extensive research and development in the use of industrial byproducts and manufactured sand in concrete. And his current research interest is in mitigation of ACR and DEF in low carbon concrete. He's also the director of UDS Boral Center for Sustainable Building and research director for Smart Reef, which is CRC, and also a member of Standard Australia responsible for concrete structure, and also a member of ACI, a proudly honorary member of Concrete Institute in Australia. And Professor Vute, please go ahead, and the stage is yours, and you can start your presentation, please.
Yes, good morning, and it's an honor to be invited to speak at this workshop. I'll share my presentation first.
Sure.
Can you enable me to share screen, please?
Interesting.
Hold on a second, participant. Oh, let's.
Okay. Oh. Okay, I think I can share screen now. Wonder whether you can see the screen properly?
Yes, we can see it, Professor Vute.
You can see it. Well,
yes.
Great. Thank you very much. I think the introduction has been made, so I'll get straight into the subject itself.
Right.
Today, I would like to share our Australian strategies to decarbonize concrete infrastructures, which I hope fit into the theme of today's workshop. Can I firstly check that you can hear me well?
Yes, we can hear you well.
Yes, and you can see the screen as well. That's great. Before we went on with it, and then just to make sure that everyone get to hear me well. So what I will cover is a VDZ decarbonization pathways, which identify a range of pathways that we in Australia could decarbonize our carbon in our infrastructures. I would then spend most of the time, in fact, talking about the innovative use of AC.
Sorry, I'm sorry to interrupt you. Can you please make the presentation the full screen?
The what? Pardon? Is that better?
Yes, it's great.
Okay, thank you for that. Yes, so the main area that I'll cover is the innovative use of SCM to decarbonize our infrastructures, before touching on very slightly on what we are doing in the accounting for our carbon capture in our existing concrete structures, and then conclude today's discussion. Now, if we look at the emission profile of the Australian cement industries, basically you can see that 60% of the carbon, in fact, is produced through a process, what we call process emission. And that is basically the calcination of limestone to produce clinker, and in that process produce CO2. But of course, there are heat and electricity that need to be used in producing cement, and that basically account for roughly 30% and 10% of the total carbon dioxide emission in total. Now, today, what I will focus on is the process emission itself, this 60% emission that you can see. Now, among the process emission, the VDSAT report. VDSAT is a company in Europe specialized in cement and concrete. And this report basically was prepared by VDSAT and supported by the Cement Industry Federation and Cement and Concrete Association in Australia to prepare this particular report. Now, in the report, you can see that they identify some 21 plus 10 plus 30, 35% of possible carbon reduction due mainly to the potential use of SCM in concrete. So this is where I'll spend most of my time in today's presentation. We also have a little 6% carbon capture in terms of the accounting for the concrete to actually absorb or take up carbon dioxide due to the carbonation process as well. So this is the area I am concentrating on. And in this, basically, I would share with you what we are doing right now to look at the introduction of low carbon concrete into transport infrastructure in particular. Okay. We work with a Department of Transport in New South Wales, which in Australia we call Transport for New South Wales. This is possibly the biggest Department of Transport in Australia because New South Wales is the biggest state in Australia. So we are working with them right now to establish a framework to expand the current the current specification that they have to capture low carbon concrete. And this is done through looking at the specification itself, looking at the improved in mix design, looking at the balance between prescriptive and performance-based specification, and finally, in introducing a new provision in the specification itself. So this is basically the framework that we are working on right now. Now, in specify any concrete at all, you would be very familiar with that. Everyone basically specify the concrete for workability, for mechanical properties, and for durability properties. And for durability properties, in fact, it's so important because this day we are looking at concrete with a specific design life, which is very, very important part of sustainability. But in doing so, I guess what we haven't got at the moment is a requirement on the embodied carbon. And that's what we're working on to say, okay, can we actually also specify embodied carbon so that we encourage the industry to use low carbon concrete to meet all the specifications that people are using. To do this, we look at the embodied carbon of the concreting materials. And very quickly, this value may differ from place to place. But I think it's what the clear important is that Portland cement is the highest, is responsible for the highest amount of carbon dioxide per kilogram of material. Roughly 0.93 kilogram CO2 per kilogram of cement used. Now, if we can replace some of it with slag have basically an order of embodied carbon lower than Portland cement, and that is 0.083, as you can see there. And if you also use fly ash, it's even another order lower than slag of 0.008. So
Sorry, can you mute your Zoom, please?
Yes. Okay. Yes. Sorry. So I guess this obviously gives us a clue as to how we can try to reduce the embodied carbon of our concrete. And I'll just show you a couple of examples.
I appreciate everyone if you put your microphone on mute, please. The guests who are joining us online today, please, I appreciate it if you put your microphone on.
Thank you. Let's look at a typical specification. This particular one is Transport for New South Wales B80 specification. I chose this one because it covers the whole range of exposure conditions. Exposure condition basically identify the environmental load that affect the long-term performance of concrete. Now, in this type of typical specification, we can see that there are usually prescriptive requirements. Let's look at B2 for cast-in-place type of application. There is prescriptive requirement on the minimum and maximum cement content, minimum and maximum water to cement ratio. It has also performance-based requirement in terms of strength, a grade 40 MPa concrete. And because this can be used in the marine type of exposure, there is also a requirement on the diffusion coefficient. And in this example, a diffusion coefficient of 3.5 times 10 to the minus 12 meters squared per second. So this is very, very typical type of specification used in Australia and possibly used in many, many other countries as well. I focus on this to start with, where they are both performance-based and prescriptive-based specification. And that basically tied the concrete producer quite significantly in what they can actually supply. Okay, so for a exposure B2 cast in place that I pointed out, I just share with you different concrete with strictly ordinary Portland cement, a concrete with 30% fly ash, and a concrete with 50% slag, just to show an example. And in this case, you'll find that we can, to meet the diffusion coefficient of 3.5, the best type of binder system in this example is the 50% slag, which basically will require, the concrete will demand an embodied carbon of around 125 kg of CO2 per cubic meter. What about the strength requirement? With a grade 40 requirement, we are looking for a mean strength of around 45 megapascal. So in this case, slag also is the mix that will give the lowest embodied carbon compared to the 30% fly ash mix or the OPC concrete mix. So to select the concrete which satisfy both the diffusion requirement and strength requirement, at the end, in this example, we would have chosen a 50% slag blended cement concrete, which produced an embodied carbon of around 220. Now, if you compare this to a OPC concrete, for instance, you'll find that we basically save about 30% of the embodied carbon. And that's the potential that innovative use of SCM enable us to choose a concrete with the lowest embodied carbon possible, which meet all the requirements. Okay. I have another example, but I won't repeat it because it would just, in this example, I guess the only thing is that the type of binder that meet the diffusion requirement and that meet the strength requirement are different. Okay, and at the end, in this case, a 30% fly ash would be the best concrete to use for lowest embodied carbon. So you need to understand the behavior of concrete very, very well to then be able to select a concrete with the lowest embodied carbon that meet both the strength and durability requirement. Am I going too fast at all? I would welcome any question so that I can clarify it as we go.
Go ahead, Professor Vute. I guess at the end of the presentation, everyone is free to ask.
Okay.
Continue your presentation.
Right. Thank you. Okay. Now, what about the different exposure? That's exposure A and B1, which only have prescriptive requirement and strength requirement, but there is no durability requirement. What do we do there? Basically, if we stick to this type of specification, the embodied carbon basically is controlled by the minimum cement content. So there isn't much room for concrete supplier to produce concrete which meet the requirement, performance requirement, but yet also will have to meet the performance-based requirement as well. So I will just quickly show this. This type of exposure usually refer to concrete that may be subjected to carbonation-induced corrosion only, okay, not a marine environment situation. So in this case, although there is no requirement on the performance based type of specification. We are doing some work to see that, okay, if we produce concrete which doesn't meet the prescriptive requirement, can we also meet the durability requirement? And in this case is carbonation-induced corrosion. And for a structure with a design life of 100 years, under carbonation-induced corrosion, it is very safe to design the structures with an initiation period of around 80 years and a propagation period of 20 years, making up 80 plus 20, making up the 100-year design life. Okay. In this case, we are looking at different concrete and different carbonation depth. Of course, to get carbonation-induced corrosion resistant, we need the quality of the concrete as well as the cover depth, which will control the design life of the structures. I'll just show you this example without going too much. Basically, under the current prescriptive requirement, we would only be able to meet the requirement for in situ concrete, which provide greater cover than precast concrete, which demand lesser cover type. So very quickly, conceptually, I won't have time to go into detail, but basically to look at how perhaps we can introduce a performance-based requirement to enable producer to come up with a novel solution which satisfy the performance requirement and perhaps do away with some of the prescriptive requirement in terms of minimum cement content, because it's the minimum cement content that control largely the embodied carbon. Now, most of this would be is the concrete with high SCM content that may be subjected to high carbonation. So all this work is to enable concrete with high SCM to be designed to meet the performance requirement. Okay, so the example I show you right now is the effort to, at the end of the day, increase the requirement in the specification in terms of the embodied carbon. An embodied carbon level that can be supplied by concrete manufacturer, which satisfy these three main requirements, which we always have. And that is the workability, the mechanical properties, and the durability properties, which related to the design life that we need. Okay, I stress that strongly. Now, to look at that, there are a lot of things that we need to consider, which I, again, have explained during my presentation. In the case of strength control embodied carbon, can we use strength as an indirect control for durability? Was early strength early or 20-day strength more important? This is quite important because for precast concrete, for instance, concrete suppliers do not produce concrete just to meet the 7-day and 28-day strength requirement. They actually develop concrete that meet the strength requirement for them to strip their formwork, which means a strength at perhaps 8 hours after casting, so that they can use the formwork again and again, which is also part of the embodied carbon in the production of concrete. So, yeah, there seems to be a lot of noise here.
I'm so sorry. I'm so sorry, Professor Vute.
Yep, that's all right. I'm just sorry that maybe some people.
Actually, I've asked many times to put their microphone off, and I will ask them again.
That's okay. I just don't want people to miss some of my presentation. Yep. Okay. Now, that's the bulk of my explanation. The other 6% I mentioned at the beginning as the pathway to reduce our carbon is that of uptake of CO2 into the concrete. Traditionally, we've been looking at carbonation as a devil because it may lead to carbonation-induced corrosion, as I have just shared with you earlier in terms of specification. But with the appropriate specification, we can actually make use of carbonation because, in a way, the concrete structure is the base carbon dioxide sink, carbon sink. And therefore, we are now working toward how to account for the CO2 that our structures is actually absorbing. These are very important data because this is what the Intergovernmental Panel on Climate Change, hopefully with the data available from different countries, will propose this as part of the carbon capture from our concrete structures. Okay, so concrete has always been looked at as basically the devil in producing CO2 and so forth. In fact, concrete structure are also doing the good part in absorbing CO2, similar to plantation and so forth and so forth. So this is also the type of work we are doing right now. So I'll just conclude my presentation that at the moment, our strategies that we are already working on is that we will look to specify embodied carbon in our concrete specifications, as I explained. And in some cases, especially in carbonation-induced corrosion issue, we would be looking at the development of performance-based specification to tackle this issue and also to enable a novel solution to be used to lower our embodied carbon. And finally, to account for the CO2 uptake as part of the carbon sequestration that would be used by the IPCC, the Intergovernmental Panel on Climate Change, to put, I guess, the positive image of concrete rather than the negative image that everyone talking about. So that's the end of my presentation. Thank you very much for your attention.
Thank you so much, Professor Vute. It was an interesting presentation. And please, if anyone has questions, let me know, and we will ask Professor Vute.
May I ask just a few questions, please?
Yes, of course.
Stop sharing.
Thank you so much, Professor Vute. Of course, all your research contribution is not hidden from anyone in Sydney and internationally, as well as everyone knows. I just had one question actually. As you've mentioned, durability performance of concrete is crucial when we were talking about sustainability. And one of the factors that you've mentioned was diffusion coefficient. Just not aware of this form of like, what is it, diffusion coefficient?
So the question is, what is chloride is diffusion coefficient? Sorry, yeah. For I guess one of the most severe deterioration for concrete structures is due to chloride-induced corrosion. Now, the transport mechanism for chloride into concrete is through the process called diffusion. Okay. Diffusion is a process where an iron moves from one area to the other area to the difference in the concentration of the particular iron. So for marine structures, as we expose to sodium chloride mainly, okay, in the seawater, the surface of concrete is subjected to a fairly high amount of chloride ions. And therefore, whereas inside the concrete, the chloride ion is controlled to nearly a zero level. So this process of chloride transporting into the cover depth can be measured by this factor called diffusion coefficient.
Thank you so much. Taking the notes for the future research.
There are a lot of work done in this area, and I can certainly share some of the publication in that area of work with you.
Thank you so much. I think Dr. Ahmed also has a question for you, Professor Vute.
Yes,
Hi.
I'll read. Oh, sorry.
Yes. Hi. How are you, sir? Thanks so much for your great presentation in the very hottest topic all around the world. Actually, reducing the carbon dioxide percentage in the concrete is the main goal for all the countries now all around the world. So my question is, these percentages, optimum percentages that you showed for slag and fly ash has to be replaced with the cement. Will it be based on the other mixed proportions such as cement content, SiO2 in the fly ash, CaO in the fly ash, the curing time, water to cement ratio?
Of course.
Based on these?
Yes, definitely so. I merely show a set of data. Incidentally, the fly ash in Australia is equivalent to the ASTM class F fly ash. Okay.
Yeah.
In general, the slag, I guess, is similar requirement all around the world. So the particular set of data was shown, and it's only applied to that specific set of materials.
So I want to learn from your presentation. So I have to consider when I'm replacing the cement, I have to consider the CaO and CaO2 content in these two additives, such as slag and fly ash. Is that correct?
For fly ash in particular, you do. That's why I mentioned class F fly ash, ASTM class F. If you use ASTM class C fly ash, with a higher calcium oxide content, you would have a very different performance altogether. So there is no fixed formula for the use of a particular SCM. You do need to do trimix and then look at the performance data individually.
Totally agree with your comment, Professor. So we have two main lines based on the standards, which is workability and compressive strength. We have to not pass these two requirements. Then, based on that, we'll be able to add these additives as a cement replacement. Thank you so much.
Don't forget the third one, and that is the durability requirement. Which is needed for to make sure that you get the service life that you wish to get from your structures.
Thank you so much.
And in Australia, our infrastructure basically demand 100-year design life, whereas for building work we usually demand a 50-year design life, and therefore it's crucial that engineers pay attention to the durability requirement, which are specific to different exposure environment. I think there's another question, written question in the chat line as well. Would you like me to answer that as well?
Yes, of course. I think this is the last one because we have time only for 3 questions.
Yep, sorry. The question is from Pshtiwan Shakor, I think. How much is the maximum percentage of fly ash could be used in concrete mixes for the same strength control, same strength concrete class with OPC, and how could be offset the strength decrease by fly ash need more water demand? Yeah, this I guess was partly answer from the first question. In a way, there is no definitive answer to that. You do need to do a fair bit of work. If you use Class F, STM Class F fly ash, in Australia, we done a lot of work there. And basically, if you only look at the strength requirement, a 20% by mass replacement seem to produce the concrete with similar strength to a pure OPC type of concrete. 20% fly ash also is very important in preventing another type of durability problem called alkali silica reaction. And that is the reaction between alkali from cement and certain reactive silica in aggregates. So in any design of concrete at all, we need to take care not just for the specific environment itself, but also the long-term performance in terms of any potential reaction between cement and the aggregates. And another challenge is in what we call delay ethringite formation, which apply very much to precast concrete. Okay, so the use of a fly ash or slag, there is so much consideration you need to take into account before you decide what is the best way to use and how much SEM would be required for that particular application. So it's a complex answer, I guess, or there's no simple formula to be used.
Thank you so much for your time and your presentation, Professor Vute. We appreciate it.
Thank you.
And before starting our second presentation, please can you make Mr. Farid Sartipi a host for the Zoom?
Hi, Doctor. If you could just look at the participants. If you click on the participants, you see a sidebar. You've got everyone's name there, correct? Can you see that? Dr. Vute, can you hear me? Dr. Vute, if you could please unmute your mic so I could guide you. Yeah.
Yes.
Can you see the list of attendees on the right side of your screen?
Yes, I can.
And if you could go to Mr. Farid's right click and make him host, that would be great, please.
I have already enabled everyone, actually. Hang on. Mr.
Farid needs to be a host. Yeah, yes. And Mr. Farid, could you make us co-host as well, if you can, please? If it's possible. If not, don't worry, carry on.
Pshtiwan, how can I make it a co-host? Sorry, right click on it or?
It's okay. It's okay, Mr. Farid, if you can.
Okay.
Okay, before starting our second presentation, I would like to introduce Mr. Farid to everyone. Mr. Farid Sartipi is a research associate in the Institute of Construction Materials, and he started his academic and professional career in construction material industry in 2015. And after completing his bachelor degree in engineering, he started an intensive 4-year industry research program by having an eye on business studies and working with multiple universities and colleges in Sydney, Australia. And his main research interest area is concrete technology, CO2 capture, and environmental conservation and automation. Mr. Farid, you can start, and you have 20 minutes to present your.
Thank you so much for the introduction, and the organizing panel to organize this wonderful event. I'm pretty sure it's pretty informative for everyone who is attending. It's basically the latest technology in concrete that everyone can get access to and also learn from it. My research topic in the past few years was CO2 capture in concrete. Somehow a complementary type of research with what Professor Vute had just presented. Probably going to be digging deep more into the technological aspect of CO2 capture and the CO2 uptake in concrete and what technologies are there for us to reduce the CO2 emission, or basically, let's say, absorb CO2 instead of emitting CO2. There's a bit of a confidentiality notice in this presentation because we are partnering with our industry partners, so I wouldn't be able to disclose all the technological parts of what we've achieved so far, but still there's a lot to talk about. The background knowledge of CO2 in concrete relies on two main methods, let's say, physical entrap and chemical decomposition. The physical entrap is by pressurizing CO2 gas into some parts or some ingredients of concrete. It is applicable in recycled concrete only, and meaning that if you decide to natural aggregate, this method probably won't be as effective as the second method. Low absorption rate, high cost of production relatively because of the time that it takes to produce this type of CO2 concrete, and also the limited slump flow, meaning that self-compacting concrete wouldn't achieve by that. So a bit of an older version of CO2, but still captures a lot of attention from our industry partners, especially one of the main concrete manufacturer producers in Sydney. Just seen one of the truck mixers in wearing the logo that says
دو وصل أنا تقسيم دوبه مثلا شهاني للسنة ذاك اللي نزيق مثلا
اگر زومك تعمل كان
دو زار ما نسيته ماذا والله لا أنا كريم فروشني بيقرأ مثلا اعتيادي أنا مثلا ما إيش ما بقوي بناي هنيا رقم قد عكلا جوز لك أو دو موضوعي تويس إيش ما بقول
Mr. Farid, you have the ability to mute his mic. If you could please do that, because you are the host, you could just block his mic. You could mute him. You could put him on mute. Just go to his name, and on the sidebar, you could mute him. Can you hear me, Mr. Farid?
here, but I'm trying to find.
Yeah, just go to the list of participants, and you could mute his mic. I think he's away from his phone or computer.
Mr. Farid?
Yep. Disabled now. Okay. It's all good. Okay, should I continue? Yes, I should.
I'm so sorry.
Okay. All right. So yeah, it was about the physical way of entrapping concrete and trapping CO2, meaning that CO2 molecule wouldn't be decomposed into any other type of chemical components. Rather, in the other method where we have chemical decomposition of CO2, it means that so if you start reading about CO2 capture, it's about mineralizing CO2 in some other forms, meaning that In that form, we are going to break the bonds between carbon and oxygen and make CO2 as a hazardous environmental substance, non-environmental substance, into something that can be seen as non-hazardous. It is applicable in all types of concrete, meaning that there is no restraint on the type of aggregates we can use. It's basically a liquid or type of chemical admixture we can use to reduce the CO2 emission, or let's say CO2 absorption. So if you've seen a product somewhere that says net zero carbon emission, meaning that either the life cycle assessment done on that product shows zero emission, or there is some sort of CO2 absorption in the manufacturing process that is resulted from the production of that particular product. High absorption rate can be achieved as much as you want, like 90%, 100% of the CO2 that is being injected or introduced into this chemical composition, it will be absorbed, and low cost of production relatively because of the low time of production that it takes. And it's also highly workable because it's a chemical admixture. And moving on to the next slide, I'll be talking about how do we source CO2 gas. So let's say we know that it is good to use CO2 in concrete, but how can we find CO2? That will be the topic about the next few slides. Capturing methods are, especially in Australia, we have to take a step back and see what are the main sources of CO2 emission. And in Australia, it returns back to coal power plants. The major electricity providers are sourcing the energy from the coal power plants, and that's the main source of CO2 emission. So if we go there on these coal power plants and try to implement some sort of a technology to absorb that emitted CO2, then we can make sure that the CO2 emission would be much less. So we have pre-combustion, post-combustion, and oxy-fuel combustion, which are the three main methods studied by CSIRO, Commonwealth Science and Industry Organization. Each has its own unique characteristics, but before we know what technology is more effective, what goes into details of each of those three capturing technologies, we can say that we have to know what the coal power plant looks like. So there's a feed of coal that goes inside the boiler. The coal is being burned. It boils the water. The water steam goes into the turbines, and the turbines will generate the electricity. And caused by the burning of the coal, there is a lot of CO2 gas being emitted into the environment. And that's where we can focus on, like this chimney right there. That's normally called the flue gas. Is where we can source our CO2 and take it into a good use instead of letting it being emitted into the atmosphere and causes global warming. Pre-combustion carbon capture is one of those effective methods that is proven to be, at least theoretically, effective. It is schematically shown in here. The pre-combustion methods are chemical procedures involved in the steps before the fossil fuel combustion. In this case, will be the coal. These are usually chemical gasification of the input coal, aiming to lower the amount of CO2 emission. So let's say we have coal, and we have to gasify that before we burn it. In this process, coal is combined with oxygen to produce a gas made up of carbon monoxide and hydrogen. that combination of carbon monoxide and hydrogen is also called syngas. By adding water to the syngas, CO2 is produced and captured while the hydrogen is burned to generate the power. Pre-combustion capture is potentially less expensive than post-combustion capture. So in such technology, we're not going to burn coal, or maybe they will burn coal, but what causes the CO2 emission, CO2 absorption as the result, is the syngas that is being burned and produces the CO2 for us. We capture it and then use it in concrete, because we were talking about concrete. And it can be used in other forms as well, if like fire extinguisher capsules as well is another use of CO2. But we're just focusing on concrete. Post-combustion carbon capture is the main method that we've used for the chemical decomposition of CO2 into concrete. Fuel air goes inside the boiler. Flue gas contains 15% CO2 and 70% nitrogen, and caused by a process that is called amine treatment. We combine CO2 and a substance that is called monoethylenamine or diethanolamine or 3-ethanolamine. These are some amine absorptions. There are also other methods introduced for absorbing the CO2 by membrane. Mainstream capturing methods are listed here. You want to write them down. It's a good way to source CO2 and reduce the environmental impact of, firstly, the energy producers. Secondly, finding a way to use the CO2. Hot potassium carbonate and chilled ammonia plus ionic liquid and also membranes are another method. One thing that was pretty much noted in almost all of the research paper is the high cost associated with implementing this technology on a power plant. It was said that 30% of the energy that is produced by the power plant has to be used by this absorption method, just to decompose the absorbed CO2 that is being basically absorbed by the monoethylenamine. So monoethylenamine is absorbing CO2 and decomposes into some other sort of substances, but then you have to think about releasing that CO2 from the solution that is CO2 rich, and that process involves a lot of heating. So we're going to heat up that liquid, which results in the release of CO2 from the monoethylenamine. Heating up that liquid takes 30% of power generated by the coal power plant, so it wouldn't be cost effective. And that's why this project is not being implemented in the coal power plants. There's a lot of energy being consumed by it. But Professor Paul Ferran is a really great guy. He spent 20 years-ish on CO2 capturing methods. And he had suggested that, let me refer to the notes, so that will be really accurate about the referencing, as this is really important in academia, that the metal-mediated electrochemical process to harvest the CO2 absorption enthalpy can reduce the energy consumption. That sentence itself, I guess that can be a PhD thesis. Anyway, but there's another way also to find out, to reduce the cost of implementing this post-combustion carbon capture. Oxy-fuel combustion carbon capture is another, the third method to absorb or to capture the CO2 or source the CO2. In simple words, we are burning coal at the exposure of 90% pure oxygen, and that is emitting a high concentrated CO2 instead of having nitrogen in the syngas or in the flue gas. We're having a complete CO2 concentration, so it will be easier to capture and absorb the CO2 later on. Another really important way of capturing CO2 is to just focusing on our own industry, being construction. We have a really polluting production process in construction called cement production. Cement production causes a lot of CO2 emission, and that's how we can approach it. That can be another possible way to reduce the total CO2 emission. So far, we know how to find and source our CO2 that is needed to be converted into some other chemical forms rather than being released into the atmosphere, causing global warming and other harmful effects. Now, the question is, how can we use CO2 in concrete? What is the concept behind CO2 concrete technology? It's been referred to as those two, physical entrap and chemical decomposition. Those are the two latest technologies, but recycled aggregate has been around for, I guess, 20 to 30 years. It's one way to recycle the construction and demolition waste. Recycling always is known as an environmental process, and we're getting pretty good results from recycled aggregate in concrete. Low-rise buildings can be built, like buildings as high as 1 to 3 levels can be easily done, being built by recycled aggregate. We can get up to 40-50 megapascals by having the right mix design. Something called geopolymer is where you can basically eliminate cement in concrete and use only fly ash and slag, which was the focus of Professor Vute research projects as well. But there is a bit of a safety issue in using geopolymer, as we are going to work with a highly basic liquid, sodium hydroxide, with a high molarity, has to be used in combination with fly ash and slag to create geopolymer, and that's not something safe to be done on site. Also, since it's eliminating the cement use in concrete, cement manufacturers are against it hugely. Cement manufacturing is $1 billion business in every country, so it's not easy to just let's say, okay, we're going to stop using cement, and $1 billion industry would say, okay, we're going to stop it today. But still, it's there. Geopolymer will get the same results without using cement. If at any point in the history, in the future, humanity decides to not use cement, that's the way to go. So I've explained these two ideas, and I guess my time is over. If there is any questions about the research, I'll be more than happy to answer.
Thank you so much, Mr. Farid, for your time and your presentation. And if anyone has questions, please let me know. Okay, sure.
Hi, Mr. Farid, how are you? This is me,
Thank you so much.
Ahmed.
Thank you so much.
I have been working on recycling aggregates and geopolymers for more than 3-4 years. My question is, this recycled aggregate, how the grain size distribution of these materials will affect the behavior of concrete?
So I'm pretty sure you know the answer, but for the audience, well, it's not something different from the natural aggregate, except that we have high water absorption. But in terms of particle size distribution, as we get finer particles, finer recycled aggregates, we can expect to have higher flowability and higher water absorption. So higher water absorption will normally result in lower strength. So it has to be decided or based on the project. It can be the particle size distribution can be determined. Normally what we use here in the laboratories on construction sites are 10 mil aggregates and 20 mil recycled aggregates. So
correct me if I'm wrong. So I have to get the D10, D30, D60 effect of these recycled aggregate concrete and then compare it with the standards based on the upper limit and lower limit of the standards. Then I will be able to use it. Am I right or wrong?
That's true. It's yeah, that's exactly right. Like any other concrete product, it has to be compared and validated with the existing standard, and it falls into those specifications every time. It depends on the mix design as well.
Okay, thank you very much. Thanks a lot. You have a good day.
Thank you so much.
Thank you so much. We have another question.
Hi, Farid. Pshtiwan speaking. Just wondering regarding those methods that have been used, like oxy-fuel, if this is really practical for absorbing or reducing the CO2 emission in a concrete, or this is just like a theory can be used? If there's any application, there's any like a research have been done for that purpose in a maybe in a cement plant?
I'm not sure about the cement plants, but there are some pilot plants on the coal power plants to absorb the CO2 from the coal power plant. So it's not directly being used in concrete. But one thing, referring to the oxy-fuel method that you've mentioned, not sure if it's been ever used in reality. It's in theory. It's been done in the laboratory, shown the effective ways, but post-combustion carbon capture methods are being used in Western Australia, in Perth, at the small scale. Yeah, and another way to reduce the cost is to not heat up the monoethylenamine CO2 reach, because of the heat consumption and the rising cost of CO2 absorption. It can be directly used in concrete.
Yeah, thank you so much for your great presentation.
Thanks for organizing this.
And we have the last questions.
Dr. Farid, thank you so much for the presentation. Actually, I don't know whether to ask you or Dr. Vute if he is available. I just wonder, in order to contribute in reducing the CO2 emission or the embodied carbon dioxide in concrete, I think there are research done in using natural admixtures to be incorporated in concrete. Do you aware of using the most popular or the natural material, especially fruit, tree extracts, and etc., to be used with concrete in order to take part in reducing the CO2 or the embodied carbon in concrete? Thank you so much. You or Dr. Vute can answer the question. Thank you so much.
I don't have proper knowledge in natural admixtures, so.
Yeah, well, I'm not sure exactly what admixture you're referring to, but the use of any chemical admixture, of course, have a big role in reducing the water requirement and hence the cement requirement. And therefore, chemical admixture has been used for many, many years in reducing the cement content and therefore embody carbon. Now, with this range of natural admixture, I am not sure whether it works in a similar way or not. But if it works in helping to reduce the water requirement, then the concept that we understand from the use of chemical admixture would apply.
Thank you so much, Dr. Vute. And thank you so much, Mr. Farid, for your presentations. It was great. Thank you so much for your time.
You're more than welcome. Thanks for organizing this. I learned a lot from Professor
Really
Vute.
appreciate your time and your great presentations. And later we will send a certificate through a link that we have sent you. Thank you.
Okay, great.
I think it's over. Is it over?
Okay, just
Yeah. Student is over here, but I think I cannot.